So infinitely repeated games are complicated objects, and the strategy spaces are vast. Any mapping from histories to future to current actions, and so it's not surprising that there's a great many of equilibria that they can give rise to. Question is, can we somehow say something about all those equilibria, somehow characterize them? And the answer is yes, or at least we can characterize as the sort of payoffs one can achieve in any equilibrium of the repeated game. We will look at what are called folk theorems. They're called folk theorems because they were sort of known in the folklore for a long time before anybody actually bothering to write them down and prove them, and nonetheless they're very important. It's theorems, or if the purists will say theora, because they come in many flavors. We will look at infinitely repeated games with the limit average reward, but there are versions that exist for many other settings, for finitely repeated games, for games with future discounted rewards, for versions of repeated games that are actually games of incomplete or imperfect information, and others. But they all have the same similar structure. Here is the intuition. Take any one-shot game, a stage game, and imagine that all agents but one gang up on the remaining agent. What's the worst thing they could do to that remaining agent? It's, by definition, hold that agent down to his security level or max min value in the game. That means that they could, in principle, enforce any strategy profile, that is, any strategy for all of the agents, that such that if everybody played that strategy, that remaining agent would get at least his max min value. And they do it by essentially threatening in the strategy to, if that agent ever played anything but what that strategy profile prescribed for that agent, to go and gang up on him and hold him down to his max min strategy. So the poor agent has no choice but to do that. We sometimes call this the trigger strategy, or the grim trigger strategy. That is a strategy that something triggers the punishment. So consider prisoner's dilemma. There are only two agents. So what sort of punishment can one of the agents threaten the other agents with? Well, that agent could say something like, "I'm going to start by cooperating, but if you ever defect, then from that point on, I'm going to defect forever." Unlike tit for tat, where if you defect once, I'll defect once, but then I'll revert to cooperating if you indeed cooperated. Here, if you ever renege, if you ever defect, then from then on, I defect forever. That's why we call it the grim trigger. Well, that's a very severe threat. Now imagine that all agents, or in the case of prisoner's dilemma, both agents have this mutual threat. They can both threaten to hold each other to their security level by defecting forever. If the other person defects, well, that has force. And the question is, how can you use that to characterize the equilibrium of the game? So from the formal point of view, let's start with any stage game, G, and let's imagine its infinite repetition. We'll call that G prime. And look at any payoff vector. So we are going to play this game, and we're now thinking about the one-shot game, G, and we'll say that the payoff vector R, consisting of R1 through Rn, is enforceable. Is essentially every agent in that payoff is getting at least his or her security level or max min value. And the intuition here is that surely if they're getting less, then you can't enforce it, because they can unilaterally do something and it'll give them something larger, namely their min-max value. And so the intuition is that we really should restrict our attention to enforceable payoff vectors. Another notion of feasibility. This means we're looking at the set of payoffs. Are they at all achievable in the game? Again, we're talking about the one-shot game here. And obviously, if they're not achievable at all, then they can't be part of an equilibrium because they're not part of any strategy profile. Now, this is a little subtle. We're going to speak about achievable under rationally mixed strategy, meaning that the mixtures are mixtured by rational numbers, not arbitrary real numbers. And that's a technical condition that's needed that we'll gloss over. But given these two definitions, we get a rather remarkable connection between the payoffs obtainable in any natural equilibrium of the repeated game G prime and the payoffs obtainable in the game G. And here it is. It says that if a payoff vector R is an equilibrium of the repeated game G prime, then it's got to be enforceable. Again, that is not that surprising, this only if condition, because again, if it's not enforceable, it means one of the agents is getting a lower payoff than they could in any of the state games on their own. And of course, if they can get it in any stage game, they could get it repeatedly over and over again, and therefore get it as the limit average also. And so it makes sense that you'd have to restrict yourself to enforceable. What is perhaps more remarkable, that it's not only a necessary but also a sufficient condition. So if R is enforceable, and let me skip the feasible for a moment, then if it's enforceable in G, then it's also an equilibrium of the repeated game G prime, and that's rather remarkable. And we need this as an added condition of feasibility. And again, I'm glossing over the details here, but if you go back to our intuition, what's our intuition here? That the agents will all but one agent will make sure that the other agent is kept honest. Namely, they would get their payoffs, which has got to be greater than what they could get on their own, so long as they played according to this prescription. Well, it's better be the case that this payoff that being offered in effect achievable over time as the limit average converges, and therefore you have to do it. It has to be done through a mixture over time, and the definition of feasibility that appears to the rational mixture needs that condition. That's the intuition about the Folk theorem. And just a final note that, as I said at the beginning, there are many other versions of Folk theorems, and in particular what concerns us here is that there are Folk theorems that have to do not only with the natural equilibria but also with the subgame perfect natural equilibrium in the repeated game. And the intuition there is you look at punishments that aren't infinitely extended in time, but that are doable, that are meted out over a finite window. And if you look at the punishments that are achievable in a finite window, you get a version of the Folk theorem that is relevant there. Similarly, there is a version of the Folk theorem that holds for future discounted reward. And here the main thing to point out is that they hold for discount factors that are large enough. And recall that the large discount factor means that we actually don't discount the future that much. And the intuition here is also fairly straightforward. In order for for the threat of punishment to be credible, the agents who's being threatened better care about the future enough